Good morning, everyone. My name is Brendan McGinty. I am part of the team that drives the Center for AI Innovation. Thank you for spending time with us today. We have a great presentation lined up for you on the geometry of data by my friend, Dr. Aaron Saxton. Aaron is a data scientist who works in the Blue Waters Project Office at the National Center for Supercomputing Applications, NCSA. His current interest is in machine learning data and migrating popular data and machine learning techniques to high performance computing environments. Aaron's career has shifted between industry and academic ventures, a great thing. Prior to NCSA, he was a data scientist and founding member of the agricultural data company Agrable, participating in crop model development and customer-facing deployment. Before that, Aaron worked at Neustar at the University of Kentucky and SAIC. In the summer of 2014, shortly after joining Neustar, Aaron graduated from the University of Kentucky, earning his PhD in mathematics by studying partial differential equations, operator theory, and Schrödinger's equation. Aaron, please take it away, and thank you for being here.
Great, thanks, Brendan. Hi, so welcome. As I was introduced, my talk is about the geometry of data. So let me go over a little outline real quick. I'll be introducing a little toy example and explaining some neural network basics and how we actually go about training models. And then, ways that we can visualize and interpret a little bit what's going inside this toy example. Then I'll take that those techniques and extend them to another canonical example of the MNIST data set, going through neural networks and convolutional neural networks again. So with that said, this talk, I was inspired to study this topic from a blog post by this Christopher Olah, where he studied neural networks and from the perspective of manifolds and topology. More recently, there's been a paper put out, Topology of Deep Neural Networks by Gregory Niatz and some others. So this is a topic that is a little bit abstract, and what I'm trying to do is find ways of using it to help design machine learning models so that they perform better while training them at scale. So this talk is not going to be your traditional, here's a theorem, here's the proof, and here's the paper that was all in. This is all work that's ongoing, and it's a little bit of an art form. At the moment, it's an art form. The pie in the sky dream is that we do hammer out some good, solid results. So yeah, I encourage you to take a look at some of these, this paper and these. This blog, they apply these some of these techniques to very basic examples, and what I'm going to go over is how do we take these techniques and look at what potentially could be more real world examples. Okay, so the toy example that I want to start with is a 7-segment display. In this world right now, the maker community is super popular, so you've probably seen these little electronic components called 7-segment displays. What's more is that this is a little bit of a computer vision problem, right? In the sense that us as humans have decided that if we light up these segments in a particular way, then our brains interpret that as, oh, if we light it up with lights all around the perimeter, we interpret that as a 0. If we light up a 7-segment display just with the 2 segments on the right, well, that looks kind of like an Arabic numeral 1. So we interpret that as a numeral 1. And then 2, 3, 4, and so forth. So a 7-segment display doesn't look exactly like the Arabic numerals, but it looks close enough that when we look at it, we make an interpretation. So the next nice thing about this example is that we can also encode what the segment display is displaying by looking at what I'm calling a voltage vector. So on the bottom row or bottom row here, voltage vector is just describing which pins on the back of this electronic component are pulled to high voltages or low voltages. So the voltage vector that represents an Arabic numeral 0 is 11111110. So it's saying that all the segments are on and lit except for the last one, which happens to correlate to the middle horizontal segment. And then the Arabic numeral 1 has another unique voltage vector, 011000000, and then 2, 3, 4, 5, 6, 7, 8, 9. So it's this voltage vector that we're going to use as the encoding for the input of this example. Okay, so this by itself is not that interesting. Honestly, we could just use a linear transformation if we wanted to map these voltage vectors to the digital representation of each Arabic numeral, and that's virtually trivial. So we're going to add another ingredient to this. What happens when perhaps this 7-segment display was on your old favorite college alarm clock and your kid smeared some peanut butter across it, and now it's malfunctioning a little bit. So when you wake up bleary-eyed trying to decide what time it is, it's flickering. Okay, so this is a situation where where machine learning might be able to help us a little bit. The data isn't that pure. The data has noise in it. The data doesn't look exactly like a numeral 1 or a numeral 2 or so forth. So for example, if we take the vector that represents the Arabic numeral 2, and perhaps the noisy version of it is 0.8, 0.7, 0.1, 0.8, 0.8, 0.1, 0.9. And of course, this cute little animation, even us as humans have a hard time maybe looking at that animation and realizing that that's a 2. But maybe we can build a model that will separate that out. Now, adding noise to data is not, or it comes in many different varieties and flavors. In the real world, this is often the crux of how do we build models and how do we study data. For this toy problem, I have the freedom of combining noise with the data in any way I want. So the simplest way is maybe we just add a normal distribution to, or we sample from a normal distribution and add that to all the input data. But the simplest way to maybe consider and study nonlinear data is perhaps you have 2 normal distribution random variables with different means and variances, and you only assign or you only draw from one random variable or the other depending on which digit you're considering. So if your digit is 2, 3, or 5, you sample from this distribution, and if it's everything else, you sample from this distribution. It's a simple way of studying what nonlinear noise might look like. And then you can also study things like perhaps study things like generalization and selection bias. Perhaps you thought that the hardest thing to train on might have been 5, 7, and 8. So you add a lot of noise to 5, 7, and 8, but you don't necessarily add that noise to the other digits. So your training happens on input data that looks that even though it represents the same fundamental thing, the way it looks to the model winds up being different during training than during deployment or inference. All right, so this is the toy problem and kind of the character of the data. So what can a neural network do for us? This next slide, depending on your level of expertise, might be a little pedantic, but the reason I write it all down is I want to show you the guts of what a basic machine learning model looks like, in this case, a neural network. And I want to be able to point at some of the features and tell you, this is what I'm visualizing. So with that said, On the right, this kind of line diagram with all the nodes, this is a common way of having a visual representation of what a neural network looks like. But I want to emphasize that this diagram describes very specific arithmetic, describes a very specific formula, something that we can, if we were super bored on a Friday night, we could all sit down, write down on a coffee napkin and compute if we wanted to. Albeit it would take us a long time and be super boring. So in this diagram, on the left-hand side, each one of these green circles here represent a dimension from the input data. So in this example, our input data is a 7-dimensional vector. So we have 7 nodes. So that means that, for example, up in the left-hand corner here, I took this as our example input data, the 1, 1, 0, 1, 1, 0, 1. If I remember correctly, that was a 2 maybe? I don't remember. Yeah, no, I think that was the 2. So as the arithmetic that this diagram describes is saying that, oh, we put a numeral 1 in the first circle, a numeral 1 in the second circle, a 0 in the next, a 1 in the next, a 1 in the next, a 0, and a 1. Okay, now the arrows pointing from our input layer into the first hidden layer, and I'll explain what that means a little more in a second. The way that this data flows is described by the formula I've written out here on the right. So moving from the input to the first hidden layer is this part of the formula right here. It's just at this point, it's just linear algebra. We take a weight matrix. Here it's labeled as alpha sub m, but over here it's written out in its full glory. It winds up being 2, 4, 5, 7, 7 by 5 matrix. Okay, so the first operation in a neural network is simply multiplying your input vector by this weight matrix. And from linear algebra, whenever you happen to take that, this 7-dimensional vector onto this 5 by 7-dimensional matrix winds up outputting a 5-dimensional matrix, or a 5-dimensional vector, I'm sorry. So the point I'm trying to get across is the dimensionality of your data keeps on changing as it moves through the layers of your network. Simply by the definition of vector matrix multiply. Okay, again, that by itself is maybe not that interesting. I just want to make sure that we all have in our head that that these operations will change the dimension of our data as it moves through the model. Now, the secret sauce to a neural network is this next step. So we multiply the input vector, or the input vector times the weight matrix, and then of course we add it to a bias, fine, whatever. But then we hit it with a nonlinear function. This is the thing that separates a machine learning model from just vanilla linear algebra. This nonlinear function, we call those activation functions. And they often look something like what I have plotted here on the left-hand side. This one is called a rectified linear unit. It's 0 on the left and then linear on the right. The more traditional activation functions often look like an S-curve. This was happened to be a logistic function. It's very low on the left and then gradually increases around the origin to 1 on the right. And these activation functions are applied to that 5-dimensional vector that's the result of the input data being multiplied by the weight matrix, is applied pointwise. So that means each item in that 5-dimensional vector, when it after it goes through its first operation, is made an input to this activation function. So if the weights happen to be in such a way that the multiplication gave you a 0 as one of the values, well, then the activation function would say that, oh, that's a 0.5 if you happen to use this one. Okay, so this is the first major part of the formula that represents a neural network. You have an input vector, you do some vector matrix multiplication, some vector addition, and then you apply an activation function pointwise to that resulting vector. Okay, and so what we say is that our choice here of, in this example, our choice was that we chose in this first layer 5 hidden units, or in other words, that just means that there are 5 rows to our weight matrix. And just because we have the freedom to design this model any way we want, I chose to add a second hidden layer with only 3 hidden units. And so in my second layer, this matrix here on the right side represents the weights, the weights that that will that you'll combine with the output of the first layer. So the first layer had an output of a 5-dimensional vector, and the second layer, its input will be a 5-dimensional vector. That's why we have 5 columns here. But then I chose that there are 3 hidden units, so its output is going to be a 3-dimensional vector. And then once the data flows through each of these layers using this arithmetic, eventually we need to encode it into the final result. So this toy problem is a classification problem. We're taking in a 7-dimensional vector that represents the voltage on this electronic component. And we want to take that vector and dump it into a bucket, a classification bucket. Is that vector a Arabic 0? Is that vector an Arabic 1 or 2 or 3? So the very, very output layer, we have 10 classifications, 0 through 9. So the output layer winds up being a 10-dimensional variable or a vector. And the transformation from the last hidden layer into the final output is commonly just a linear transformation. And then, of course, often hit with what's called a softmax. The formula for a softmax is right here on the left-hand side. These hidden layers, we often call them dense layers because they are densely connected to the inputs and outputs of all the other layers around them. Okay, so the takeaway from this slide is that as the data flows through each of these layers, it's the result of some linear algebra operation combined with a nonlinear activation function, and the dimensionality of the data keeps on changing. Okay, so we're going to choose a 2-layer neural network, just like in the previous slide. To study classifying this noisy input data, classifying it into which Arabic numeral does it represent. And so the only things we have to choose, us as the user, is what data do we want? All right, we chose that. I said I'm studying a 7-segment display. How many layers, how many hidden layers do we want? Just so it's a little bit interesting, I'm going to choose 2 dense hidden layers. And then how many hidden units are we choosing between each of these layers? I haven't written that on this slide, but I'll show you what we choose here in a second. And that completely determines the particular model. That completely determines the particular model and tells us exactly how many values are in those weight matrices. And so the values of those weight matrices that are unknown. You chose the data, you chose the architecture of the model, and now the crux is finding the weights, the trainable parameters that are that do the job that we want. In this case, classify each of the input vectors. Right. So what is the major technique used to find these weights? Oops. Here it goes. Well, machine learning is just curve fitting. So the mental model that will extend across most machine learning is just regression. How do we back in your college algebra class, how would you have fit a line to some cloud of data? Well, fitting a line, that statement itself says what our model is. Our model is mx plus b. And we're not looking for x and y. That's the data that we're given to you. You're given. What we're looking for is the slope and intercept, the m and b. So we need some way of measuring, some way of measuring how good the model is at for any particular value of m and b. We call these loss functions. Here in the middle, I have a toy loss function where I take the model that the linear model that we chose. I dump it into this formula and subtract it from the y value of any of the particular given data set. All right, or in other words, I look at the output of the model and compare it to what the true output is, and that gives me some error. And then I square it because I want this thing to be positive, definite, and all the nice properties a loss function should have. So the goal is to minimize this loss function. This is the loss function after everything is said and done is just a single number, a single scalar. You feed it, you give it the model, you give it whatever your initial, the architecture of the model, you give it whatever your initial unknown trainable parameters are, and you sum over all the data that you're given to train it. And all of that combined together gives you a single value. And we want to minimize that value, in this case with respect to slope and intercept. In your college algebra course, you would have done something, you would have used, actually, I'm sorry, in your calculus 1 course, you would have taken the derivative of this, set the derivative equal to, with respect to m, with respect to m and b, set them equal to 0, and then solve. And it would just be a linear algebra problem. But in practice, our formulas are much more complicated. They're the formula that I just walked through from that neural network example, where there are many, many unknowns than just your m and b. And so the main technique that we use is gradient descent. So we're searching for a minimum of our loss function, and we're taking the gradient with respect to each of the trainable parameters, each of those alphas. So let's see, in that in those previous slides, we had a 5x7 matrix was at 35 unknowns there, and then we had a 3x5, 15 unknowns, was at 50 unknowns. So the gradient on this loss function for that example I showed a few slides ago would be a 50-dimensional vector. Okay, so gradient descent, you choose your loss function. This is, and then you take the gradient with respect to each of the weights. Over on the right-hand side, this is just a fictitious loss surface. The x and y axes, these were just plucking two weights out of all of that and varying only those 2 weights. We keep we keep all the weights fixed except for 2 of them. And so if you randomly initialize your model with some particular set of weights and you only vary 2 of them, the height, the z-axis, is the value of your loss. And so if you happen to have initialized your model so that the loss sits maybe somewhere right here, the gradient will tell you the direction of your steepest descent. So it will tell you to update your weights by moving, by modifying your the alpha 1 and alpha 2 a little bit to the right and maybe down a little bit. Down on the XY axis, I plotted what's called the gradient field. So you can look at that gradient field to know what direction gradient descent is trying to tell you to to update your weights. So these arrows are pointing to the right. And so you update your weights a little bit and then take the gradient again at this new location. And then you update the weight a little bit and you update it by an amount called the learning rate, which is gamma. This learning rate can affect your the way your training behaves. For instance, if you updated the weights too much, you would step all the way over and you would hit the other side of this this lost surface. But if you update it too little, it takes a lot of steps to work your way down in here. Okay, so gradient descent says take the gradient, evaluate all your training data and at the particular weight values you have, and then that'll tell you the direction to update your weight values. And eventually, as you iterate over this process over and over and over again, the weights will find the values at which the loss function might minimize here on the right. If you had chosen different initial values, perhaps your loss function would initialize here on the left, and the optimization will tell you to, and the gradient descent will tell you to move to the left over here. So these loss functions can have all sorts of crazy, topography, and they're clearly not a unique minimum. Or in what's more, we do not assume that we find global minimums for that matter. Okay, so there's some other loss functions. The one I showed you initially, that was just a toy example to get the conversation going. A modification on that is just root mean square. And then there's also cross entropy, and there are good reasons to use one or the other. They wind up affecting the shape of this loss surface. Okay, that's all fine and good, but in practice, we use stochastic gradient descent. Back in the previous gradient descent, one thing I kept forgetting to say explicitly, this loss is over the sum of your entire training set. So that means you have to load your entire training set into memory at some point to compute the gradient and decide how to update the weight variables. Stochastic gradient descent says that you don't. Stochastic gradient descent is a modification where we only load one training example at a time. So we load one training example. We take the gradient with respect to each of the training weights, update the training weights, and then feed the next training example. Choose the next training example, evaluate the loss function, take its gradient with respect to each of the weights, and update those weights. So every time you update the weights in stochastic gradient descent, you're doing it after evaluating the model at different training samples. Now, the pure version of stochastic gradient descent says that you do exactly one example at a time. One example, update the weights. Next example, update the weights. Next example, update the weights. Unfortunately, that's a very serial process. You have to do the arithmetic at the first layer of your model before you can finish up the arithmetic at the last part of your model. So what most optimizers do is they use stochastic gradient descent with mini batch. So instead of taking up all the memory or lots of memory resources by loading your entire data set, you only load a subset of your data set, the mini batch of it. You go partition your training set into mini batches. You load the first batch, evaluate the loss function, take the gradient, update the weights, and then take the next batch, evaluate the loss function, compute the gradient, update the weights, and so forth. So when practitioners started using stochastic gradient descent, one thing we started to learn just through empirical evidence was that the models that you trained with stochastic gradient descent in small batch sizes wound up giving you faster time to solution than if you tried to load the entire data set. And this was a little counterintuitive, and it still sort of is today. It turns out that training models with small batch size gives you better generalization properties and gives them to you faster. But when we use small batch sizes, we can't take advantage of as much parallelism. And we'll go through that here in a second and really explain that detail. Okay, so here's the first bit of topology. So what I've done here is I've gone and I've chosen a model that had, let's see, which one did it have? I thought I said it in a previous slide. We chose a neural network model with 2 hidden layers, with 5 hidden units and 3 hidden units. And what I'm about to show you is when we use stochastic gradient descent with different batch sizes, it winds up having an effect on the way the loss surface looks, or the way that the way the gradient descent would necessarily follow the loss surface to find its optimum. So in the upper left-hand corner of these graphs is the loss surface when training with batch size of 128. In the upper right-hand plot is the loss surface when training with batch size of 256. Lower left, batch size of 512. Lower right, batch size of 1024. And what I went and did is I looked at all the weights in the model, and I found the weights that, quote unquote, were the most active, that during training got changed the most. More specifically, I just use an L2 norm across across the training steps, and I looked for the weights with the largest L2 norm. And so those are the weights that I plot on the X and Y axes in each of these plots, and then the vertical is the loss value. So what we see is the loss is indeed decaying. Next one and next one. Okay, so let's take a second and appreciate what we're looking at here. Indeed, in this simple model, the topography of the loss surfaces is very, very similar. However, the thing I want you to get from looking at this is that changing the batch size does indeed change the character of the loss surface. So training a model with a batch size of 128 is going to search for its minimum in a different path than if you were to train a model using batch size of 1024. Now, part of my research is to try and find striking examples of why the smaller batch size necessarily gives us better convergence properties. But what I'm trying to show you right now is that it will give you at least different convergence properties. Okay, so this is the first little bit of geometry of the data. It's a way of taking all this data and summarizing it as a single number, as a loss. And how does the algorithm stochastic gradient descent affect that loss as it steps through each of its training steps? And indeed, one of the things that really affects it is the batch size. Okay, so that's all fun and good. Now let's go back to that other detail that I was stressing. The output of each of these layers is another vector. Is another vector that has some dimensionality that we could choose. That we choose based on the hidden units. And we can so we perhaps take a numeral 4 as input, and we do the arithmetic to move that data through the first layer, and its output is a vector that's a 5-dimensional vector. Or in other words, we are projecting the input data onto a manifold in 5 dimensions. So we can capture the data as it moves through each layer of the model. And then the data is still passed to the second layer, and then we can capture it as it comes out of the second layer. So now I keep on talking about the dimensionality of these vectors. We need a way of visualizing these things. And I'm not going to do anything fancy. People in the audience might know plenty of other ways of doing this, but I'm just going to use a simple principal component analysis. There are many reasons that I prefer using this as opposed to things like t-SNE or other dimension reduction algorithms. But we're going to study a little bit of principal component analysis. All right, so a quick explanation of PCA, a principal component analysis. On the left-hand side, perhaps we had some cloud of data in 3 dimensions. 3 dimensions for us humans is pretty easy to glance at and represent, but we can still apply this technique into higher dimensions, and the principles are still the same. So if I perform PCA on this cloud of data here on the left, what it's doing is it's finding a basis which maximizes the variance. Or it's finding a basis in these 3 dimensions to project the data down onto it in such a way that it is most spread out. The philosophy is that we are able to see that this is the basis in which we see the projection that has the most features. So our human eye looks at this cloud of data, and yeah, indeed, it's kind of squished like a pancake a little bit. There's a couple clouds all over the place. I went and colored it according to some arbitrary classification. In this case, 5 different classes. It turns out that there's this purple one that's really close to the screen, and then the blue one is really far away. And so when PCA goes and looks for the basis that maximizes the variance, it does this plane here that's labeled as the blue and this pink bars. So that's the plane that PCA decided to slice this 3-dimensional plot and say that if you project the data down onto this basis, it'll be most spread out. And so on the right-hand side is the result of the PCA and projecting the data down. Now that projection is a linear transformation. There's nothing fancy about it. Once PCA decides the basis, it's what is it, a 2x3 matrix, or 3x2, one or the other. And just with that linear transformation, you already kind of see that it was able to separate out some of these classifications. Some of them are garbled together, and it's hard to understand that they're different. But like this purple one really expressed itself by itself out in the corner here. All right, so now we're going to use PCA to apply to data as it moves through the model. Okay, so let's look at what PCA looks like on these 7-segment voltage vectors. So if we just add a little bit of noise to these 7-segment voltage vectors and then project them down, use PCA and project them down into onto 2 dimensions, they just look like cute little blobs. And even if I didn't go and color the classifications, we could look at these blobs and say, oh yeah, this is probably one of the input classifications. There are probably 2 sitting here. There are probably 2 sitting here. This is kind of a garbled mess, but it's not so bad. Us humanites, even without the coloring, could probably see that this is clustered together in this and this and this. So the input data, with even a little bit of noise, we discover this principle that data has separation. That the manifold at which we project this data when there's not much noise to it, has this natural way of separating itself. The numeral 2 likes to live in this part of the space because of our choice of the way we encoded it. The numeral 0 likes to live in this part of the space. The numeral 9 likes to live in this part of the space. But little data, but none of the problems that we study only have a little bit of data. Those problems aren't interesting. Or only have a little bit of noise. Those problems aren't interesting. So this is what a lot of noise looks like when we project it down. All of a sudden, all these classifications are all mushed together. So without the color coding, our human eyes probably could not look at this and decide where each of the classifications were. Then, of course, there's nonlinear ways that you can add noise. Some of the classifications get bunched up close to, are tighter packed together than others. And then lots of nonlinear noise. All right. So now what you're looking at is the way that each of these classifications are flowing through that through a neural network model that has 20 hidden units and 10 hidden units. It turned out when I trained this model, I was able to get an accuracy of 90%. And so the animation here is how the model is behaving after each training iteration step. And so you'll notice once this loops back, when we get started, on the left is where the input data. The first one in the middle is the output of the first layer, and the second plot in the middle is the output of the second layer. And then on the far right is the output of the output layer. And so what this model is doing, what the training is doing to this model is teaching this model how to project the data in which the classifications get separated. And that's where the topology, that's where the manifold, all the topology and manifold theory come in. Is that the goal? Yes, the goal is indeed to minimize loss, but the actual action that happens is the model learning how to do the arithmetic so that the data gets projected, the data of the different classifications get projected into distinctly different regions of each of the manifolds. So you'll see in the first layer, there's a little bit of deformation, but not too much. In the second layer, you get a lot more action. In fact, let's see, the red on the far left, the red is almost intermingled with the green. It's really hard to see where the two separate. By the second layer, though, the model has learned how to deform all the red classifications, away from the other data. Okay, so that's all fine, good. This was done with a 2-layer neural network with 20 hidden units and 10 hidden units. Let's say we use a smaller network. Smaller networks presumably are faster and easier to compute. So, for compute resources, you would want to use a small network. However, the smaller network winds up having a harder time pulling data apart. You'll see that after the first layer, okay, yeah, it's still kind of doing something interesting. But after the second, it winds up projecting everything into, many of the classifications into these 2 lines here, and leaving you with these linear artifacts. What's going on here is that because we have so few hidden units, there are not enough degrees of freedom to continuously deform the data apart from each other. So this is one way that we can look at these visualizations and say, oh, our model probably doesn't have enough capacity. Our model probably isn't big enough to solve this problem. So already we have some guidance on, after talking to you guys for 45 minutes, this is the first piece of guidance we have for interpreting for a geometric interpretation of the data as it moves through the model and making some type of actionable decision. Oh, the manifolds that it's projecting onto doesn't express enough of the features. So perhaps we are using too small of a model. The accuracy happened to be around 60%. All right, what happens when we use way too big of a model? Hidden units of 200 and hidden units of 100. We got a little better of an accuracy. We got 97%, but we increased the size of our model by an order of magnitude and only gained 7%. Well, looking at the way that that the training is teaching the model how to deform the data, there's really not that much action going on. It seems like with this large of a model, it stabilizes pretty quick, or it has projected this data into such a high dimensional manifold that the linear the linear way you would separate all these two things becomes almost trivial. But you have to work with a model that is an order of magnitude larger. So this kind of visualization allows us to try and find the Goldilocks model, one that's not too small, that doesn't have enough degrees of freedom, but one that's not too big, that we're sort of wasting resources. We could have spent those resources iterating through the training faster. All right, so we're getting close to time. I'm going to race through this this next example. Up until now, I've been using my little toy 7-segment example. It's kind of neat. It has a natural explanation, high dimensional vector spaces, and that's great. However, the CAII is using machine learning for computer vision, so for images. So we're going to look at the MNIST data set. The MNIST data set is a standard data set of handwritten Arabic numerals. They are 28 by 28 pixels, and they are a single channel, so they're grayscale. So let's use a neural network again. Looking at the loss surfaces. So if I remember correctly, the neural network I used here was a 2-layer and probably 20 hidden units and 10 hidden units. So here's one of the principles where we're using the exact same model, but on 2 different problems. And already with this input data being such higher dimensional, the different batch sizes winds up affecting the loss topography quite a bit more. And you'll just have to believe me when I say when I tell you that the larger batch size winds up not generalizing as well. But at very least, you can see that it has a big effect on what the loss surface looks like. All right, let's see how it winds up projecting the data through the model. If I remember correctly, this was this was the model that worked really, really well on the 7-segment display. This was the 20 hidden unit and 10 hidden unit. And it's pretty active as it's deforming all these, while it's training, it's deforming all these clusters around. But it winds up having a hard time by the final layer really separating anything out distinctly. If I remember correctly, the accuracy wound up being something around 80%. Okay, so neural networks will get the job done for MNIST, but let's introduce a new ingredient, convolutions. Convolutions in machine learning are virtually identical to convolutions from signal processing. They're a way of taking 2 functions, combining them, and creating a 3rd function. And they do it by pointwise multiplying each of the functions together, with one being translated by a certain amount. And so in this animation, one of the functions is the red line. We often call this the kernel. One of these functions is the blue line. We often call this the signal. And then this black line that showed up here is what the resulting new function looks like. This particular convolution happens to be what a rolling average it looks like. Oops, oh, I should have taken that out. Okay. So if we want to take this principle and apply it to images, what we do is the kernel, in this case, is just a 3x3 array. We can choose it to be any size, but for this example, let's just choose it to be a 3x3 array. And it turns out that if we chose the values of this kernel to be 0, -1, 0, -1, 5, -1, 0, -1, 0, the arithmetic of the convolution means that you take this window, you put it on your image somewhere, and you multiply the value, you pointwise multiply the values of your kernel by each of the pixels in this window, and then you add it all up. That's exactly what the formula was from the previous slide. You go pointwise multiply, and then you add it all up. And you walk through and you do, and you stride your window across this entire image, and you're able to create a second image, just like the convolution before. You take two functions, you put them in, and you get a third one out. So image convolutions, you take two functions, the image and the kernel, you perform this arithmetic on them, and you get another image out. Now, classic image processing have decided that this particular image kernel does what's called a sharpen operation. And so it sharpens the image. It does the opposite of blur. Let's look at this on a larger image. So what is this? The New York Public Library image. So if we apply that, that convolution kernel to the New York Public Library, sure, that image got a little sharper. But these kernels can have other effects. For instance, the image processing community decided that this -1s with 8 in the middle detects outlines. It probably detects where the image changes a lot. And so that transforms the image into what we see here in the upper right, where we where the stark changes really get highlighted. So convolutions can have lots of different effects on images. Which ones are the best effects? We don't know. We're going to let the stochastic gradient descent choose. So the reason I write all this down, the actual values in these kernels are trainable parameters. So we're going to let stochastic gradient descent learn and decide which values those trainable parameters should be. All right, so convolutional neural network, we would take the input vector. In this case, it's one of these images. We apply two-dimensional convolution against it, like what we just saw in the previous slide. Max pool, I haven't talked too much about this. This is just looking at a window and finding the maximum value. And then we perform another convolution, then another max pool, and then on the very last layer, we do a dense neural network layer. So this first model here is what a model designer would have might have chosen just at a knee-jerk reaction: 2 convolution layers and some max pools. From the visualization I'm about to show you, it turned out that this one sucked. No, it didn't suck. It just the visualization kind of indicated that there were resources being wasted. And it turned so after modifying the model, the second model I'm going to show you the results of is where we just had a single convolution layer and a single dense layer, and we wound up getting better results. Okay, so let's take the tour. So this is the better results. Already we added a new ingredient into our model design, and the topography of the loss functions already changes a little bit, or quite a bit. You get these little pinches in the middle, these cusps. The literature out there indicates that this is a little bit of the result of convolutions. You can ask me about that later if you want to. This is actually really, really interesting that it's doing this. But again, the big takeaway from these slides is varying batch size, you wind up getting very different loss surfaces. And you have to believe me when I tell you that the larger the batch size, the worse the convergence properties. Left is the input, right is the output. Let's see, PCA projection, layer 1. So the first convolution does a little bit of deformation, it flips it around a lot. And then the this layer in the middle is a reshaped layer. Nothing real is going on there. That's why I graded out. And then on the far right is, is the dense layer. Another thing we see from this visualization is that early in the training, the convolution is really learning a lot. Where near the end of the training, the dense layer is still trying to figure out how to optimize the way it's separating the data. And we see that the green classification and the pink classification get a good separation. The way this was projected, some other things look piled up on each other. So that's the good one. And I'm picking up pace because I realize I'm running out of time. Now here's the bad one. Or in other words, throughout the training, even at our first layer, it doesn't do very much. It doesn't do much. It doesn't deform the data. It doesn't learn how to deform the data in any particular way. Or in other words, it's just taking whatever its initial value was, which was more or less random. But by the time you get to the lower layers here, they are more active. And so that was the motivation for clipping out a lot of this. So by looking at this visualization, we got some clues onto how to modify the model architecture to get some bigger bang for our buck. All right, so key takeaway, large batch size has effect on loss surface. Empirically, large batch size results in poor stochastic gradient descent minimizer. Layers project data between manifolds. Stochastic gradient descent finds weights that do this in a useful way. Good models, quote unquote, separate data. And all of this is to find Goldilocks models. Not too much activity, not too little, and not too little. Okay, so I am technically out of time. The reason I kept on stressing batch sizes is because that's the way that distributed training works. Is it takes an item from each of your batch sizes. So if you have a large architecture or a large computing architecture, and you want to distribute it across here, for example, if you had 4 nodes, your minimum batch size is 4, because that sum in the during the gradient descent all happens through some collective. So if we want to scale our models, or if we want to scale the training on larger and larger compute architectures, we have to design the models so that they can handle larger and larger batch sizes. And one way that I'm currently investigating designing those models is looking at the way the data projects through the layers and how well the model is able to separate data and how the loss surfaces evolve through training. All right, sorry I had to rush there at the end. I hope you guys got something out of this.
Aaron, thank you so much for your time. What an amazing presentation. A lot to digest, obviously. What I've done is put your email address in the chat, we do have one question. Does the geometry of data interpretation allow to estimate the number of nodes in each of the hidden layers?
The short answer is that's what we want. There's another number I didn't talk about called the capacity of a model. The naive way of computing the capacity is just looking at number of number of weights or number of degrees of freedom. However, because because each of these weights aren't independent, right? They're connected by the arithmetic, the formula of what, for example, the neural network was. That's why the degrees of freedom, that's why the number of weights isn't exactly what the degrees of freedom is. So the hope here is that this isn't a direct measurement of capacity, but it is a way of estimating whether the model's capacity or its degrees of freedom does indeed match the problem. But as you can imagine, data sources are messy. There's no good statistics or math statement. That's one detail I didn't have time to talk about, is in the original papers of stochastic gradient descent, there are strict conditions on when that thing converges. However, the types of data that we use on these models, rarely is it easy to to compute those statistics. For example, what is the variance of an image? There's no good way of computing that.
All right, excellent. That's all the time that we have. Again, Aaron's email, saxton@illinois.edu. If you have any other follow-up questions for him directly, thank you so much for taking time today, and we will see you next time. Thank you. Aaron, again, thank you.
Thanks, everyone. I hope it was useful.